In this lab, I will discuss the physical properties of a falling object and the forces acting upon it. I observed an object falling, and then using Newton's second law, I created computational models of the falling object with and without drag force. Comparing the models to my observations, I found that the model with drag force better matched my observations. I also found that only the model with drag force would reach a terminal velocity. For my observations, I filmed a sticky notepad falling down from rest. I used Tracker software to create a series of position versus time points for the falling pad, which are shown on the right side of the Tracker interface. My axis was oriented so the negative y-axis was in the direction of the falling pad, and the origin is at the center of the pad. The computational models I made to predict the motion of the object are based on Newton's second law, which relates the forces acting upon the object, net force, to its velocity over time. In the code, Newton's second law is used in the form velocity final equals velocity initial plus net force divided by mass multiplied by change in time. Once final velocity is obtained, the new position of the object is found using the equation position final equals position initial plus velocity multiplied by change in time. In the model without drag force, we assume the Earth's gravity to be the only force contributing to net force. The Earth's gravitational pull results in a weight force on the object equal to negative gravity of Earth times the object's mass. Notice the weight vector is in the negative y direction. The weight force vector will be the same at every step of the process, 0, negative 0.4410 newtons, because the gravitational pull and the mass of the object are constant. Drag force is 0, therefore the net force is equal to the weight force and is constant. In the model with drag force, both the air and earth are assumed to act on the object, making net force equal to the weight force plus the drag force. Weight force is calculated the same way as the previous model, but we must now also calculate drag force. For this model, we assume drag force is proportional to the velocity of the object squared, shown with equation drag force is equal to b times velocity squared. B is a constant that varies based on the properties of the object. Using trial and error to set this model's final point to the observed final point, B was found to be 0.0268. Notice that drag force is only in the positive y direction. Our object's velocity is not constant, so drag force will not be constant. Net force is also no longer constant. In my code, initial velocity was set to 0 as the moment the object is dropped, it is not yet moving. Mass was set to 0.045 kilograms, the weight of the pad. Change in time, the time step in the model was set to be very small, 0.001, to allow for many calculations of the changing net force and velocity. This is the graph of the observed and model y position versus time points. Observed points are shown in blue with the line connecting. The model without drag force is shown by the red line, and the model with drag force is shown by the green line. The model with drag force predicts the observed values very well, while the model without drag force does not predict the observed values in the second half of the graph. This indicates that in reality the pad was experiencing drag force. This graph shows the calculated velocity versus time points for the models with and without drag. This is actually the derivative of the previous graph. The velocity of the model without drag increases in the negative direction at a constant rate. The velocity of the model with drag does not increase in the negative direction at a constant rate, and over time the magnitude of the velocity increases less. The magnitude of the acceleration decreases. This can be explained by considering each model's net forces. The only force contributing to the net force in the model without drag is the weight force. As the weight force is constant, its net force is constant, and it has constant increase in velocity, or constant acceleration. Velocity always increases, and a terminal velocity will never be reached. The model with drag force's net force includes the weight force, which is constant, and the drag force, which increases as velocity increases. Over time, as the negative weight force and positive drag force cancel each other out more and more, the magnitude of the net force decreases, which results in less acceleration for time. Eventually, the weight and drag forces will completely cancel each other out, causing net force to be 0. When net force is 0, the object's velocity is constant, and this constant velocity is called the terminal velocity. If the object was thrown down instead of dropped, its terminal velocity would not change. The throwing of the object exerts a force on the object for only a moment. For our purposes, it is as if the object simply starts with a greater initial velocity, as if this point was now the 0 time point, rather than the 0.15 time point. The net force would reach 0 at the same terminal velocity regardless of its initial velocity. The changing velocity would still follow the same trend line and reach the same terminal velocity.